So last time I forgot there was a couple more pages of the interesting carboxylic acids and nitriles. We're going to look briefly at the salts of carboxylic acids. We'll find that there are several that are used commonly as preservatives. One that is commonly used is sodium benzoate. So look on packaged foods, particularly items that are processed foods and things like that. You'll often see sodium benzoate as a preservative, and it does show up in soft drinks as well, pickles, those kinds of things. And then potassium sorbate, also used in packaged items, helps that food to just stay fresh longer. So those are some useful salts of carboxylic acids. We'll also find that there are some useful nitriles. We talked about some of the cyanohydrins back in chapter 18. We're going to look at a couple of interesting drugs, useful drugs that have been prescribed over the last couple of decades. This one, Arimidex, is a commonly used breast cancer treatment, so helps to increased survivability from breast cancers. Lexapro is a very commonly used depression treatment. It's a SSRI. And also, this one's used for certain types of heart disease, high blood pressure, angina. And so Verilin is commonly used there. And you'll see that these all have these cyano groups on there. All right, so on to section 19.5, and we're going to talk about aspirin and related compounds, so things that are related to aspirin. So aspirin is acetyl salicylic acid. If you've ever taken aspirin, then you've taken the buffered version of this. This is a carboxylic acid. And if you take buffered aspirin, it's going to be a combination of this and its conjugate base. So there will be both of those things present. If you take aspirin and it's not buffered, that tends to increase the acidity in your stomach a bit much and can lead to upset stomach. They are similar in structure to salicin, which is isolated from widow bark. You'll see that there's this acetal linkage and a sugar. I'm not sure exactly which simple sugar that is, but it is connected to this. And then the key difference here is it's not a carboxylic acid. It is a benzyl alcohol. All right. And if we look at, so that's the salicin. If we look at salicylic acid is structurally similar to aspirin. In fact, when they synthesize aspirin, they usually start with salicylic acid. You can isolate that from meadowsweet, and it does have a sweet flavor to it, particularly the sodium salicylate, which is the conjugate base of it, it's a sweet carboxylic acid. It can be used as a sweetener, it's a natural sweetener, but it's different than sugar. All right, I'm going to just ever so briefly look at arachidonic acid and prostaglandins. So aspirin will help to decrease inflammation by blocking a certain biochemical pathway. So there is this compound that is called arachidonic acid, which occurs naturally in your body, and it's kind of interesting. It's got 4 of these cis carbon-carbon double bonds. That's one of the interesting things about it. And in the presence of cyclohexanol, sometimes you'll hear this referred to as like COX-1 or COX-2. So cyclohexanol will convert that into various prostaglandins. And when it does, those prostaglandins send signals to your brain to tell you, oh, there's inflammation, you should feel pain. And so your brain sends signals, saying, oh, this hurts. Well, one of the things that aspirin does is it helps to inactivate that cyclohexanase and make it so that you don't get as many of these signals to your brain that it hurts, and it also decreases inflammation. There are some prostaglandin analogues that have been synthesized, and I'll just point these out. These these are a little bit more stable than your typical prostaglandins, and they have been used for a number of things, but these two have been used to reduce eye pressure in people who have glaucoma. So very important drug, and you'll see the only difference between these. This one's an ester, and this one is an amide. Oh, and there's a double bond that's different there. So there are a couple of things that are different. Okay, so now we want to get into this section where we talk about the preparation of carboxylic acids. And there are a number of ways to prepare carboxylic acids, and we're going to go over some of them. Some of these are review, things that you've seen in previous chapters, and some of them are a little more recent. I don't know if there's any new ones here. Let's go through it. So this is something we saw back in chapter 12. If we take a primary alcohol and oxidize it with chromic acid, we can get a carboxylic acid. And it can be either the chromium 6 oxide, it can be potassium dichromate, sodium dichromate, sulfuric acid, and water are added to those, and we will get a carboxylic acid. We can also oxidize benzenes, alkyl benzenes, with potassium permanganate. As long as there is at least one benzyl hydrogen here, you can break that apart and get it to form the benzoic acid. So this is a useful synthesis, one that you probably want to keep in mind when you're looking at synthetic pathways. You can prepare carboxylic acids from alkynes. We talked about this way back in chapter 11. If we do oxidative cleavage of an alkyne, we will get, with ozone, we will get carboxylic acids. So if you have an internal alkyne, you cleave it and you'll get two carboxylic acids. If you have a terminal alkyne, this half that has the carbon on it will give you a carboxylic acid, but the other one, that terminal carbon, will give you carbon dioxide. This is actually kind of a convenient way to chop off a carbon. If you have one too many carbons and you want to have one fewer, you can do the ozonolysis and get that carbon dioxide. That other one leaves as carbon dioxide. So let's look at number 11. We'll go to our in-class assignment. Pull this down a little bit. All right, so we want to see what precursor gives this. Now, for some of these, there will be more than one answer. In this particular one, all we need is the primary alcohol. So A is going to be equal to benzyl alcohol, and that will give you this carboxylic acid. So you could potentially use an aldehyde. So that aldehyde you can oxidize to a carboxylic acid using this same reagent. So either of those will work. Probably would be the alcohol, but you may have the aldehyde. In that case, you can make that carboxylic acid. All right, if we want to use ozone, this is ozonolysis. This is what we just saw on the presentation. So in this case, B is going to be equal to, so since this has two carbons, we're making two equivalents. It would simply be the two butynes, or but2-ine, if we want to give it the proper name there. So we'll chop this in half, and we will end up making both of those carboxy groups. All right, for this one, here we're using permanganate, and we just need something that has at least one hydrogen. So we need an alkyl group that has at least one hydrogen. So C could be this, NO2, and then here, as long as it has at least one hydrogen, it could be that. But I'm going to put plus many others. And by that, I mean if it's any alkyl group that has at least one hydrogen here, it will work. So this could be an ethyl, it could be an isopropyl, and like I said, there's many, many options that are available there. All right, so here we're if we want to make this, we can make this from some precursor. We can use this chromic acid solution. So we're at chromium 6 oxide, sulfuric acid, and water. And so in this case, D, there are several options that this could be. So it could be the ketone to start with, but all right, but we'll go ahead and write it as an alcohol. So 1, 2, 3, 4, 5, 6, 7. So there are 7 carbons. 1, 2. So we could have this diol, and that would definitely do it. So 1, 2, 3, 4, 5, 6, 7. So there's 7 carbons there. That would give you that. It can also be, put or. You could also have an aldehyde here. All right. And you could have it where it was already a ketone. So if that were a ketone, it wouldn't oxidize it any further. So there are a couple of other options. I'm just going to put these 2, though, for purposes of this. All right, here we've got magnesium, and then carbon dioxide, and then acid to protonate it. So usually when we're using magnesium on something, and then we treat it with carbon dioxide, and then the acid, we're probably making a Grignard reagent. So E would probably just be the halide. It could be chloro or bromo. I'm going to do bromo. All right, so we'd have an ethyl group there and then an ethoxy group. And if we use bromo, that will make the Grignard reagent, and then that Grignard reagent could react with carbon dioxide to give a carboxylate, and then the H3O plus would protonate it to make the carboxylic acid. All right, this one's cool. We talked about this one. This is the Tollens conditions, Tollens test conditions. And the thing I really like about this reaction is that it's very selective, and it gives a very cool effect where it plates out silver onto the inside of your flask. So 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 carbons. So F is going to be equal to 1, 2. And so to make the carboxylic acid, this will selectively convert aldehydes into carboxylic acids while leaving these other things completely alone. So if we had a ketone, it won't affect that. And then if we had this secondary alcohol, it will not oxidize that. So this one is pretty selective for carboxylic acids getting converted, or I'm sorry, aldehydes getting converted into carboxylic acid. So very, very cool reaction. So let's look at carboxylic acids and their reactivity as acids. Now, they are reactive as acids. The hydrogen is quite acidic. In fact, this is in fact one of the most important properties of carboxylic acids, is that they are in fact Bronsted-Lowry acids. We can think of it like this: as long as we have a sufficiently strong base, we can treat that carboxylic acid with that base. It will deprotonate it, and we will get the conjugate acid of that base and the carboxylate. So easy reaction to do, and there are lots and lots of choices to do it with. It is technically possible for carboxylic acids to act as bases, where they could accept H plus from something else. To do that, you're going to need a pretty strong acid. So we don't normally think of these things as bases, but if you have a strong enough acid, like for example sulfuric acid, you can protonate it and you will get a reactive species. Here we've got 3 resonance structures, one where the double bond's here and we have the positive charge on oxygen, one where we have the positive charge on carbon. You'll notice the carbon doesn't have a full octet there, and then one where there's a positive charge on the other oxygen. These will all contribute. That middle one is not going to contribute as much, but it is important because there is a significant partial positive charge on carbon in this species, it makes that carbon more electrophilic. So it makes it more electrophilic. And so there are a number of things. If you were to protonate the other oxygen, you would get H2O plus, and that would not give you the additional resonance structure, so that one is not going to be as favorable. All right, now we want to think of carboxylic acids as electrophiles. So it is possible, if we have the right kind of electrophile, the right conditions, that we can make the carbonyl carbon act as an electrophile. So a nucleophile would come in and react with it, and we get our tetrahedral intermediate that we have seen many, many times. This either usually gets protonated, or we have something act as a leaving group. So there's any number of reactions that potentially could happen. So because it's sp2 hybridized, we'll find that the angles here are about 120. And in the result of doing this, we're going to break the pi bond. So this is typically an endothermic step. All right. So they are strong organic acids. This is what we were just talking about a minute ago. So the carboxylic acids can act as just normal Bronsted-Lowry acids. And if we have a strong enough base, we can deprotonate and get the carboxylate anion. Now, one thing that I do want to point out is that nucleophiles often can be pretty good bases as well. So if your nucleophile is very basic, it's probably going to do this and not act as a nucleophile. And that sometimes can be a problem. We do have ways to work around that, like converting it to something else, or we can add a catalyst like an acid or something. All right, so let's look at the carboxylic acids as Bronsted-Lowry acids again. So they're relatively strong acids compared to some of our other things. So they're relatively strong acids, and they will form these resonance stabilized conjugate base. So when you deprotonate, you will get this as one of your structures and this as the other structure. Our hybrid is going to have partial negative charges on both of the oxygens. If we look at the bond lengths for the conjugate base, this one is acetate, but it's going to be true for other carboxylates. We're going to find that the bond length for the carbon-oxygen bond in the carboxylate is going to be about 127 picometers, or 1.27 angstroms. That's right between a carbon-oxygen single bond at about 1.36 angstroms and a carbon-oxygen double bond at about 1.27. That tells you that these really are about 1.5 bonds. So we have about 1.5 bonds of bonds between the two carbons. So how acidic are these carboxylic acids? Well, the way that we measure how acidic something is that we look at the pKa. Remember, the lower the pKa, the more acidic. I'm going to say that again. The lower the pKa, the more acidic. So here we've got an example. Acetic acid has a pKa of 4.8. So it's moderately acidic. And if we treat it, again, with a strong enough base, in this case, sodium hydroxide is a fairly strong base, we can deprotonate it, get the carboxylate, and the conjugate base, which is, or the conjugate acid of hydroxide, which is water. In order to determine what direction the equilibrium will lie, we need to look at the acid on each side, and then look at the pKa. The one that has the lower pKa, in this case acetic acid with a pKa of 4.8, has a lower pKa than the pKa of water. So whichever one has the lower pKa, the equilibrium will lie in the opposite direction. So what we'll find is that in order for a base to be strong enough to deprotonate this, it needs to have a pKa greater, or its conjugate acid needs to have a pKa greater than about 4.8. And we'll just go with about 5. If it has a pKa greater than 5, the conjugate acid of whatever it is we're working with, then we're going to get significant deprotonation. On this one here, we've got benzoic acid. Benzoic acid, it's a little bit stronger acid than the acetic acid, but it's definitely stronger than the conjugate base of, or the conjugate acid of bicarbonate. The conjugate acid of bicarbonate is carbonic acid, has a pKa of 6.4. That's definitely a big enough difference that the equilibrium will lie to the right. Again, look at both acids, whichever one has the lower pKa, the equilibrium will lie in the opposite direction. Now, before we go on from this one, bicarbonate has an additional advantage as far as acting as a base, because when you convert that bicarbonate into carbonic acid, that carbonic acid will decompose and give you carbon dioxide. And so this is the same thing as if you mix baking soda, which is this, with vinegar, you get all the bubbles. Those bubbles are going to be when the carbonic acid decomposes, because you're going to make a whole bunch of that carbonic acid. All right, so here are a variety of bases that we can use to deprotonate. All right, so we can use these to deprotonate. And again, the higher this number is, the more the equilibrium will lie to the right. Bicarbonate is certainly enough, but these other ones, ammonia, carbonate, let's see, sodium alkoxide. So here's sodium methoxide and sodium ethoxide. And then here is hydroxide for water. Gives us water there. And then sodium hydride is definitely strong enough. This one's kind of overkill, but it'll do the job. So let's look at number 13. All right, so here we've got the question. Given the pKa values in Appendix C, which of the following bases are strong enough to deprotonate acetic acid? So which ones are strong enough to deprotonate acetic acid? So what we need to do, we'll look up the pKa for acetic acid. We actually know that one. So CH3COOH, that one has a pKa that is equal to 4.8. So 4.8. Anything where the conjugate acid of these things has a pKa greater than that should be enough to deprotonate. So it should be strong enough. So let's write down our base for each of these. And our bases are fluoride. And this one is, that one's tert butoxide. So CH3, 3CO minus. And then CH3 minus, NH2 minus, and Cl minus. So all of those things are the bases. So let's go ahead and write down what the acids are. The acid, or the conjugate acid, we will say, the conjugate acid of that is HF. Conjugate acid of this is CH3, 3COH. For this one, CH3 hydrogen, or CH4. This one is just NH3. And then this one is HCl. And we're going to write down the pKa of each of these. And so the pKa of HF, we'll need to go find that. I'm going to go back over here. And there we go. I'll bring that up. So this is Appendix C. It's in the Smith textbook. And I'm going to go ahead and open that up a little bit. All right, so let's go ahead and we'll find these. We'll find HCl first. So I'll go back to the document camera here. HCl was -7. Okay. And then for fluoride, HF. HF is going to be down here a little bit. There it is at 3.2. Okay. And then this is the alkoxide, and it is tert butoxide. I know it comes in at 18, but let's find it right there. There is the potassium tert butoxide. So again, I'll go back to this list. So HF is 3.2. The tert butoxide is 18. And then the C, let's see, let's do the NH3 is right there at 38. So 38 for, 38 for the NH3. Let's go ahead and fix that real quick. And then our last one here is the CH4. It is at 50. Now, there's a pretty good chance that you have some of those memorized if you've been following along. But if you don't have them memorized, that's not a huge deal. And so here we're going to look, is it strong enough? Well, this one at 3.2, since that's less than the 4.8, that means fluoride is not strong enough. So we'll put not strong enough. All right, so not strong enough for that one. 18, that one's definitely strong enough. So we'll put strong enough. At 50, that one is crazy strong, so definitely strong enough. All right. So ammonia at 38, that means NH2 is a really strong base, so we'll say definitely strong enough. And then finally, chloride, its conjugate acid is HCl, pKa of -7. That's a really strong acid, so Cl definitely not strong enough. So hopefully going through those, that'll help you to realize which things are going to be strong enough and which things will not be strong enough. All right, so we're going back to the presentation. And we want to look at the acidity of some common organic acids. And so this is going to include not just carboxylic acids, but we want to compare some other acids that we run into. So for carboxylic acids, we can explain why they are acidic by looking at the resonance structures of the conjugate base. So let's compare this to a couple of other acids. Now, we wouldn't normally think of ethanol as an acid, but in organic chemistry, it's an acid when you put it in with a strong base. It's an acid, so we'll consider it in that respect. So so we do need to look at the stability of the conjugate base. We're going to find, and this goes all the way back to chapter 2 of our textbook, anything that stabilizes the conjugate base is going to make your acid more acidic. So anything that stabilizes the conjugate base makes the starting acid more acidic. So the conjugate base of ethanol is ethoxide. The conjugate base of phenol is phenoxide. And the conjugate base of acetic acid is acetate. So let's look at those things. So we're going to start with ethanol. So ethoxide is the conjugate base of ethanol. When we look at that structure, we've got the negative charge on the oxygen, which, that makes it somewhat, stabilized. But you'll notice that there's nowhere to really delocalize that negative charge to. So all of the negative charge is on that one oxygen. So there's just not much to stabilize that negative charge other than the fact that it's an oxygen. We'll find that with acetate is resonance stabilized, which I will show you in a moment. It's resonance stabilized, which makes it more stable than the ethoxide, which is why carboxylic acids are more acidic. Next, let's look at phenol. With phenol, the conjugate base is phenoxide. So here's phenol, and then here is phenoxide. We've deprotonated the OH, and we've made phenoxide. Well, one nice thing about phenoxide is that we can delocalize that negative charge into the ring. So here we've delocalized it and put it on carbon 2, carbon 4, carbon 6. And then here is, we go back to our other version of the regular resonance structure. So with all 5 of those resonance structures, that tells us that we've got multiple ways, or we can spread out that negative charge over more atoms. So if we look at the hybrid structure, we will see that the negative charge is delocalized from the oxygen partially to 3 carbons. And in doing that, that's what makes it more acidic. The pKa of phenol comes in around 10. It depends on what's attached to it. Some things will make it more acidic, some things will make it less acidic. All right, so this is just sort of a quick summary of the acidity of some of our organic acids. So we'll look at the acetic acid here with a pKa of 4.8. It's the most acidic, and that's because we have 2 resonance structures, and both of those resonance structures put the negative charge onto oxygen. So we delocalize that negative charge over 2 very electronegative atoms, so 2 oxygens. When we look at phenol and phenoxide, well, the conjugate base of the phenol, the phenoxide, here we delocalize the negative charge to carbon atoms. And while those resonance structures are important, having more resonance structures isn't necessarily better than having 2 really good resonance structures. So we will find that putting that negative charge on the carbon doesn't do us as much good as putting it onto the oxygens. And then with ethanol, that one's our least acidic, we only have the 1 oxygen that we can put the negative charge on. We can't delocalize that anywhere. And so that's why that one is significantly less acidic than these others. But it will be deprotonated with a strong enough base. So now we want to look at something that we call an inductive effect. And the inductive effect is what happens when we put electron withdrawing or electron donating groups onto a known acid. So we're going to start here with acetic acid. We know that the pKa of acetic acid is 4.8. So it is a moderately acidic carboxylic acid. So a pKa of 4.8. Well, if we put electron withdrawing groups adjacent to the carbonyl, those electron withdrawing groups can help to stabilize the conjugate base. And so here we've got a chloro in the 2 position, and that helps to pull electron density away from this carbon, which pulls it away from this carbon and helps to stabilize this negative charge. And in doing so, that's going to give us a lower pKa. And remember, lower pKa means it's a stronger acid. All right. Conversely, if we use electron donating groups, well, the electron donating groups we're going to use here are methyl groups. We've got 3 methyl groups, and you will see that those 3 methyl groups, they add electron density because methyl groups are electron donating. So they add electron density to this carbon, which helps to destabilize our carboxylate for this. And that means this one is a little bit less acidic than acetic acid. Now, you'll notice that's not a huge difference. We had a much bigger difference when we put the electron withdrawing groups on than we did when we used the electron donating groups. All right, so just a little bit more on inductive effects, and then we're going to do number 34. So if we increase the number of electronegative substituents, we can make the acid stronger. So we saw this one a minute ago where we had a pKa of 2.8 on 2-chloroacetic acid. Well, if we put 2 chloros on there, so 2,2-dichloroacetic acid, then we can make it even more acidic. You'll see the pKa drops by 1.5. That's a pretty significant number. So we make it even more acidic. If we put 3 chloros on there, so trichloroacetic acid, will decrease the pKa even more. And at this point, we're almost into strong acid territory. Not quite, because typically we need to get into negative range to really consider something a strong acid. But this is going to be pretty acidic compared to just regular old-fashioned acetic acid. So we'll also find that the more electronegative the element is, the bigger the effect. So here, if we compare the chloroacetic acid with fluoroacetic acid, fluoro is a more electronegative atom, and it pulls more electron density away and makes it just a little bit more acidic. All right, there's also a proximity effect. And so here, if we look at these butanoic acids, where we've got 4 carbons in the chain, if we put the chloro on carbon number 4, so it's 4 steps away from those oxygens, you'll see that it does have a lower pKa than just regular butanoic acid. Regular butanoic acid comes in at about 4.8, 4.9, and having that chloro several steps away brings it down to 4.5. If we bring it 1 step closer, we get 3-chlorobutanoic acid, and that lowers the pKa a little bit more. But we'll get the biggest effect if we put that chloro on the 2 position. And putting it on the 2 position will pull electron density away even better. So inductive effects, there is a proximity effect. The closer that electronegative atom, the more acidic it's going to be. So let's look at number 34 on our in-class assignment. So here's number 34. There is a number 24, but we're going to come back to that one in a few minutes. So here is number 34. So match the pKa values with the appropriate structure. And here we've got the pKa, 0.28, 1.24, 2.66, 2.86, and 3.12. Essentially, what we're doing here is we're ranking these. The most acidic number, the most acidic one, is going to have the lowest pKa, and the least acidic one will have the highest pKa. So when we look at these, and I want you to take a second, maybe pause the video, look at these and figure out which one do you think is going to be the most acidic. All right, now that you've had a chance to pause the video, we're going to say this one is the most acidic. It's got 3 fluoros, and they are on 3 fluorines on that carbon that's adjacent. So they're in close proximity, and we have more of them. So this one is going to be 0.28 for the pKa. All right, I'm going to go ahead and put most acidic. All right, let's go ahead and look at the other structures. So this one has 1 fluorine, this one has 2. So we're going to find this one's going to be less acidic, and this one will be a little bit more acidic than this one, but less than this one. So this one has iodine, and that one has bromine. So those are going to be the least acidic. So let's do these. We'll do the 1.24 for this one, and for the fluoro, we'll do the 2.66. All right, for the iodo and bromo, well, bromo is a little bit more electronegative than iodine. And so when comparing those, we would say that the iodine is going to be the 3.12. 3.12. I selected the wrong one. I'm making all kinds of errors here. All right, so 3.12 for this one, and that bromo is going to be the 2.86. All right, and so this one will be the least acidic. All right, so that is how we can rank those. So let's look at substituted benzoic acids. So substituted benzoic acids. Remember, if you go back to chapters, let's see, 16 and, is it 16 and 17? Let's see, 16 and 17, and then we did 18. No, 17 was carbonyls. So if we go back to 15 and 16, we're going to find in chapters 15 and 16 where we talked about benzene, aromatic compounds, and putting electron donating and electron withdrawing groups on them. Well, we're going to find that when we put these substituents on there, electron donating groups are going to destabilize the carboxylate. So benzoic acid, where our group is just hydrogen, we just have hydrogens attached. Benzoic acid is going to have a pKa at 4.2. If we put an electron donating group on there, that electron donating group is going to add electron density to this ring and make it more negative. That is going to destabilize our carboxylate, which is this. And anything that destabilizes the carboxylate is going to make this less acidic. So we should expect a pKa greater than 4.2. So we should expect a pKa greater than 4.2. When we do an electron withdrawing group, we're going to get the opposite effect. So with an electron withdrawing group, that electron withdrawing group is going to pull electron density away from the ring. That's going to make it more positive, and that will help to stabilize the conjugate base, our carboxylate, because the conjugate base has a negative charge on it. So we can stabilize this by pulling electron density away. All right, and so now let's rank the substituents that we can have that will affect the pKa of benzoic acid. So groups that donate electron density are going to make it less acidic. They will have pKa's that are greater than the pKa of benzoic acid, which again is 4.2. And these substituents that pull electron density away, which includes a lot of things, these are going to help stabilize our conjugate base, which is going to make our acid more acidic. It'll have a pKa less than 4.2. So let's look at number 39 on our in-class assignment. All right, so here's number 39. We want to rank the following compounds in order of increasing acidity. So let's evaluate what kinds of compounds we have here. So here we have a phenol. Phenols are not as acidic as carboxylic acid, so we know that this one is not going to be the most acidic. All right, here we have two carboxylic acids. We'll rank them last. And then here we've got a benzyl alcohol. Well, a benzyl alcohol, we should expect a pKa somewhere around, pKa somewhere around 16, because it's just a typical alcohol. So, so that one is going to be the least acidic. So we'll say D is the least acidic. Phenols typically fall in at around 10, so I'm going to put approximately 10. With this nitromethyl on there, that nitromethyl is probably going to make it a little lower than 10, but not a whole lot. All right, so the nitro group is somewhat electron withdrawing. And then here, but it's not directly attached, so it's not going to have a huge effect. All right, here we've got a carboxylic acid, and we've got an electron withdrawing group. So we'll think that that B is going to be more acidic than C. So A is a phenol, should have pKa in there. Benzoic acid is about 4.2. So this one we would expect the pKa to be less than 4.2. And this one with an electron donating group, we would expect it to have a pKa greater than 4.2. So we'll say that C will be less acidic than B. All right, so absolutely less acidic. This one is a little bit more acidic. So B or D, then A, then C, then B. All right, now extraction. So we can do extraction with these compounds. We can do extraction with these compounds. So extraction is a technique for separating substances based on differences in solubility. We can incorporate acid-base reactivity into this to improve our extraction. So we're going to start with two immiscible liquids. And the two immiscible liquids that we're going to be working with are going to be water and dichloromethane. So water and dichloromethane. All right, so sometimes that's called methylene chloride, but we're going to call it dichloromethane. All right, so dichloromethane is more dense than water. And that's because with the chlorine groups in there, it makes those compounds have a density greater than 1. Most organic compounds have densities less than 1 gram per cubic centimeter, but these, it'll have a density greater than 1, so it will be on the bottom. And then the water will be on the top. So if we take these two things and put them into a separatory funnel, then you can separate them out. You can shake them up, they will separate, and our heavier layer, our more dense layer will be on the bottom, and the less dense layer will be on the top. I know my students in my on-campus course use this separatory funnel multiple times. This is a commonly used item in organic chemistry lab. If you are just doing it online, you may not have had a chance to use a SEP funnel, which I'm sorry. All right, so let's start by separating benzoic acid from sodium chloride. So separating benzoic acid from sodium chloride. Well, benzoic acid is it's a fairly large compound. It's a fairly large carboxylic acid, and so it is going to be soluble in organic solvents like dichloromethane. Sodium chloride is not going to be soluble in dichloromethane. It will be quite soluble in water. So this is going to be pretty easy to separate these two compounds. So benzoic acid, it'll be soluble in the organic solvent dichloromethane. The sodium chloride will dissolve in water. If we take a combination of the two immiscible liquids, the dichloromethane and water, and we put it in with this mixture, we're going to find that the benzoic acid, and we shake it up, right, because that's what you do with the separatory funnels, you shake it up. The benzoic acid will easily dissolve in the dichloromethane, and the sodium chloride will easily dissolve in the water. And so this will be very easy to separate. So since they are immiscible, we have two layers. We just let them separate out. The more dense layer is going to be the dichloromethane. We let it go to the bottom, and we drain that out. And when we drain it out, we will have dichloromethane with benzoic acid in it. The less dense layer, which is going to be water, will have sodium chloride in it. All right, so you can once it's in the separatory funnel, then you can separate the two layers and put them into separate flask, and you can evaporate the solvents, and that would leave by, when you evaporate the dichloromethane, that would leave behind your benzoic acid, and for the sodium chloride, that would be in the water. Easy enough. All right, so this is a very easy separation. So now what we want to do is we want to look at separating benzoic acid from cyclohexanol. All right, well, cyclohexanol is soluble in dichloromethane as well. So if we put both of these into dichloromethane, we're going to find that they are both soluble in dichloromethane and that they are both insoluble in water. And you might think, well, that makes it impossible to separate. Well, I wouldn't be showing you this if it were impossible. So they're both soluble in the organic solvent, and they're both insoluble in water. So if we were to put this into our SEP funnel, we would find that they would both go into the dichloromethane and nothing would go into the water. So how do we go about separating this? Well, this is a chapter about acids, all right, carboxylic acids, and we know that carboxylic acids will react with bases. So if we were just to treat this mixture with a base solution, we would find that we could separate it then. Let me show you how. All right, so there's a significant enough difference between the acidity of the benzoic acid and the cyclohexanol. If we use a base, and the base that we're going to use would be something like sodium hydroxide. When we treat that mixture with sodium hydroxide, the sodium hydroxide is a strong enough base to deprotonate the benzoic acid and convert it into sodium benzoate. Well, sodium benzoate is insoluble in dichloromethane because it is ionic, and it is quite soluble in water. So by treating it with the base, we're going to make our benzoic acid into sodium benzoate and make it soluble in water. And this is how we separate it. We can tell which direction the equilibrium would lie since we chose sodium hydroxide. Sodium hydroxide is a sufficiently strong base. You'll see here pKa of 15.7. That's definitely strong enough to deprotonate our benzoic acid. All right, so here's the summary. We've got both things dissolved in dichloromethane. And then we add, we'll just pick 10 molar, or 10%, not 10 molar, 10% sodium hydroxide solution, which is a pretty strong solution. So 10% sodium hydroxide solution, and we'll find that when we shake this up, that will deprotonate the benzoic acid and cause that benzoic acid to go into the aqueous layer. Then it's just a matter of letting it settle, and we separate the layers. The lower layer is going to contain dichloromethane and cyclohexanol, which we can evaporate off the dichloromethane and get our cyclohexanol back. And then we can take our benzoic acid in water, or sodium benzoate in water, and that will be in our other container. Now, if you want, at this point, you could add some acid to this solution, and that acid would cause this to come out of solution. And so that would be one way that you could isolate it. All right, one last thing that we want to talk about related to sulfonic acids. So sulfonic acids All right, so sulfonic acids, as I was mentioning, I had to pause there for a second. Sulfonic acids have this structure where they have an alkyl group attached to a sulfonic acid functional group. So this is the sulfonic acid functional group. We have seen sulfonic acids in the form of toluene sulfonic acid, TSOH. We've talked about that multiple times, so that is toluene sulfonic acid. It is a pretty strong acid. It has a pKa of -7, which is equal to the pKa of hydrochloric acid. What that tells us is that this is a pretty strong acid. The reason we don't include it in the normal list of strong acids like HCl, HBr, HI is that, well, the number one reason we don't include it is that it's not super soluble in water. You can get some to dissolve, but it's not as soluble in water. All right, I had to look it up. It is fairly soluble in water, but it's just a different acid. This one, you can get about 67 grams to dissolve in 100 milliliters of water. That's pretty darn soluble. So toluene sulfonic acid is pretty soluble in water. But in any case, we typically don't include it in our list of acids because it's just kind of different. We're going to find the reason that it is so acidic is that when we deprotonate it, so when we deprotonate the toluene sulfonic acid, we get the conjugate base. And those conjugate base, if we look at it, we've got 3 oxygens that we can delocalize that negative charge to. And with those 3 separate oxygens, all 3 of those are very electronegative, obviously. And so that provides us with a very stable conjugate base, which is why this is such a strong acid. So let's look at number 24 on our in-class assignment. So we're going to go back over, look at number 24. It was actually before 34. It just kind of got moved around. So we've got 2 other commonly used sulfonic acids are methane sulfonic acid, which is CH3. All right, so that's methane sulfonic acid, and trifluoromethane sulfonic acid, which is CF3 sulfur OH. All right, which of these has a weaker conjugate base? And the one that has a weaker conjugate base is going to be the stronger acid. So our stronger acid is clearly this one that has the three fluoros on there. Those 3 fluoros help to draw electron density away and from the conjugate base. So that means that this will be the weaker conjugate base. So CF3 SOO minus is the weaker base. All right. And then which conjugate base is a better leaving group? Well, Same thing. Whichever one is the weaker base is also a better leaving group. So. All right, and then which one of these has the higher pKa? So finally, this one has the higher pKa. All right. Oh, well, of the acids, this one has the higher pKa. So higher pKa. And when we say higher pKa, that means it is less acidic than the other one. So this would be the stronger acid with a lower pKa, and this would be the weaker acid with the higher pKa. All right, well, we're going to stop there. Again, we're at about 55 minutes on this video, so we're going to stop there, and the next thing that we're going to look at is amino acids.